Hello, Mr. Collier here. Today I'm going to give you some notes about energy and matter, which is from Chapter 2 in your chemistry textbook. Energy is defined as the capacity to do work or produce heat, and there are lots of different types of energy. Not necessarily asking that you memorize all these types, but just be aware of what they are and be ready to recognize them. I do, however, want you to be able to identify the two main classifications of energy that all those others will fit into, and that's kinetic energy, which is the energy of motion, and potential energy, which I'll talk about in a minute. So a couple examples of kinetic energy would be like thermal energy, which is the energy of particles in motion, or mechanical energy, which is the energy of larger things in motion. The other type of energy then is potential energy, which is stored energy. It can come from position, like being high off the ground, or it can come from something like a string being taut on a bow. It can come from the electrical potential energy in like a battery or a strike of lightning, or just from being high off the ground like in this roller coaster. So there's lots of different ways to store energy. Potential and kinetic energy can go back and forth. So if you throw a ball into the air, for example, it has kinetic energy when it leaves your hand, and it has potential energy as it reaches the apex of its flight, but then it gains kinetic energy as it falls back down to the ground because of gravity. And another key idea from energy is that it can be transferred from a system to its surroundings. It can change form and it can go from one place to another. So for example, photosynthesis is when light energy turns into chemical energy through the process of biology. There's lots of other energy transformations. For example, you plug something into the electrical outlet and it makes something else hot. You eat food and you can use it to power your body and pedal a bike. Or you put gasoline into a car, which is stored chemical energy, and it can turn into the mechanical energy of your car driving. So energy transformations are all around us. These energy transformations can be described as endothermic or exothermic. When these changes absorb energy, we call that endothermic, and when they release energy, we call that exothermic. So for example, hand warmers are going to release energy. They're going to feel warmer. That's considered exothermic. These instant ice packs are going to absorb energy and get colder. That is endothermic. We can measure energy using a variety of different units. One is called the calorie, which is the amount of heat it takes to raise 1 gram of water by 1 degree Celsius. And another common one, which is the SI standard, is the joule. Both are units for energy, and we'll talk more about them as the year goes on. But the bottom line when it comes to energy is that it's conserved. It's not created or destroyed, it just changes form, which is why talking about those energy transformations is so important. Another way we can measure this energy is by measuring temperature, which is a transfer of heat. Temperature itself is a measurement of heat or kinetic energy, how fast on average the particles are moving in a substance. There's several different temperature scales we might use this year, a little bit of information on them. So the Fahrenheit system is really only used in America and a couple other small places. The most common one throughout the world is Celsius, and it's used by scientists. But the Kelvin system is actually the SI scale, and it's considered an absolute scale. So anytime we need to do math in this course, we're going to be using the Kelvin scale. The boiling point of water in the three systems is slightly different, 212 in Fahrenheit, 100 in Celsius, and 373 in Kelvin. And then we can also look at the freezing point of water across the three systems. This is not necessarily information that you need to memorize, but I do think having a general background of how these systems compare will help you do better this year. For example, understanding that 20 degrees Celsius is about room temperature, while 37 degrees Celsius is about body temperature, will go a long way for understanding a measurement that you might take. And of course, absolute zero is the coldest possible temperature, where we need to look at where our scales relate, and Kelvin is unique in that it has no negative numbers, so it starts at 0. Here's just a couple graphics looking at the comparison of the different temperature scales. Something interesting is that the Fahrenheit scale is one that has different values. So to go from freezing to boiling in both Celsius and Kelvin is 100 units. When you look at Fahrenheit, it's 180 units. So each degree in Fahrenheit is worth a different amount than it is in Celsius and Kelvin. Another graphic showing how different temperature scales compare, specifically Fahrenheit and Celsius, just to get you more familiar with it. And one last one. So there is a conversion between Celsius and Kelvin. We did this in our last chapter, so you should be somewhat familiar with it. And the 0 point on the Kelvin scale is called absolute zero. All motion of the particles stop at absolute zero. Therefore, the kinetic energy is zero, and hence the term absolute zero. It can't be any colder than the particles completely stopping. Which brings us to our final slide here. Did you hear about the man who got cooled to absolute zero? He's okay now.